All right, so as I mentioned that we have pretty much covered the entire data path, the single cycle data path, but we need to talk about the control signals, how these control signals are generated. So here is the path that was missing because the immediate generator generates the 12-bit value, and it is then shift left to 1 to retain to recover the missing 0, the rightmost 0, and then depending on whether the branch instruction, the branch condition satisfy or not, this PC source signal will decide whether the next PC will be the one in sequence or the branch instruction. Okay, so the PC source decide where is the PC source coming from, the next instruction, which is displaced by the 4 bytes, or the branch instruction, which is being calculated here. Okay, so ALU operation, which is this one, this 4 bits. Remember how does this 4 bits? I mean, what do we use it for? To decide whether the operation that we want to perform is an add operation, and or subtract operation, or operation. Okay. So these 4 bits are not generated directly. Rather, we generate an ALU operation first. Okay. What does that mean? Let me include the controls module here. So this is the enhanced version of the diagram, the processor diagram, with the control module here. So all what we need is an opcode to decide what will be the values of these control signals. So with the help of the opcode, control signal will decide whether it's a branch instruction, what should be the value of the mem read. Either we are reading a memory or we are writing the register data from the memory, and then mem write signal, ALU source, and reg write. We are generating 2-bit ALU op signal based on the opcode, which will help us decide what will be the 4-bit output of the ALU control. So first of all, why are we splitting this? Why cannot we just generate a 4-bit signal and wire into this ALU directly? The first thing is, in order to directly analyze it, we not only need to analyze the opcode, but also need to analyze func3 and func7 fields. Okay? When we are analyzing more bits, what does that mean? We need to make more comparisons, like if-else structure. Okay? And generally, you can say that if-else structure is implemented with multiplexer. More multiplexer means more digital gates. More digital gate means it will cause more delay. So it will not be faster if we compare func3 and func7 field here. Okay. Another important thing is designer would like to split the control. We would not want to have the entire control given to one unit, because if that unit fails for some reason, the entire thing fails. Okay, so that's why we want to have a distributed control. So that is one of the other reasons. Okay, so let's talk about generating ALU op signal first, based on the opcode. Okay, so again we are learning the subset of the instructions, not we are learning the hardware for a subset which are commonly used, like add or subtract, these kind of instructions. We are not going to cover everything, cover the hardware for everything. So the simple implementation. So what does ALU do when there is a load or store word instruction? What does ALU do in case of load and store instruction? What operation it performs? Addition between offset and the base address, which means that the base address is coming from the register and the offset is again an immediate data. Okay. In branch instruction, it performs subtract operation. We have already discussed this, and we are specifically talking about BEQ. Okay. And in R-type instruction, F depends on the function fields. Okay. So this is the thing which we have discussed long ago about these operations. But as I said, ALU operation is generated in 2 steps. So first of all, if it is a load word instruction, depending on the opcode, ALU op signal would be 2 bits 0 0. For LW and SW, ALU op would be 0 0 in both cases. For BEQ it is 0 1, and for R type it is 1 0. Now R type could be add and subtract or anything, okay? Which means that if the instruction is R type, then we have to look into func3 and func7 field, okay? So we are not looking into func3 and func7 field in the control unit. Only if it is needed, then we will look into the those fields in the ALU control, okay? So if the instruction is LW or SW, the generated signal ALU op, the 2-bit outputs here, which the control signal generated, would be 0 0, okay? If it is branch instruction, the generated value of ALU op would be 0 1, okay? And if it is R type instruction, again depending on the opcode, then we have multiple possibilities. We can the instruction can be add instruction, or instruction, and or subtract instruction. So in that case, it generates ALU op 1 0. The value here generated is 1 0, and then we look into the func3 and func7 field also, okay? Look at this table. So ALU op is derived from the opcode. So we have the opcode for LW, SW, BEQ, and R type. So in R type we have add, subtract, and OR. Only in that case we look into the func3 and func7 field. In above 3 cases, it does not matter whatever the value of func3 or func7 field, okay? It does not matter. Any question here? Now compare this thing with the func3 and func7 field for these instructions. So ALU op, when it is 0 0, it means it's a load instruction. So it will generate 0 0 1 0 operation. So 0 0 1 0 operation corresponds to addition operation, which will perform the addition between whatever value we provide an input of ALU. Okay, it is usually in load and store word instruction, it is always the RS1 plus the base offset. In case of 1 0, okay, so in this case we need to decide, in case of 0 1, it's a subtract operation which will be specified by the branch instruction, and in case of 1 0, when it is 1 0, then we need to look into the func3 and func7 field, because we have to decide whether to perform add operation, AND operation, or subtract operation. But if you carefully, okay, so before that, these ALU op values cannot be 1 and 1 together, okay? So the control unit, this control unit, is not going to generate the value ALU op 1 1, okay? Now assume that the value is 1 0, okay? It is 1 0. So we have to look to the func3 and func7 field now, okay, to decide what operation to perform. If you look at here, the func3 field, they are different in all 4 cases. But here, you see, these values are all same from bit number 25, I25, to I29, all zeros, all are same. Then I30 is changed, but I31 is also same. They are all zeros. When the values are same, do we need to really check them? We can just discard, and we do not need to compare them. So all what we need is 1 bit in func7 field, which is I30, 30th bit in the instruction, and 3 bits in func3 field, okay? And that is why in designing a digital hardware, it is important to design the truth table first. So you can discard what is unnecessary or what is not needed. When you discard those things, your hardware will be optimized. Less number of components will be used. You can make the hardware, design the hardware as faster as possible, okay? So what we can do is we can just discard those things, yes?
How did you know you could discard them?
So by looking at this table, where the func3 fields, we know the func3 field, where do these values come from? We have already discussed this when we were discussing about the instruction encoding. Okay? Remember the 32-bit instruction format? We had the func3 field and func7 field. We had different values for each instruction. So we have just written those values in a table here. So func3 field for addition operation, let's say this one is the add operation, subtract operation. What is the value of the func3 for subtract? What is the value of func3 for AND operation and OR operation? Okay. Similarly, we have written the func7 field for the same instructions. By writing all those values, you can see these from bit number I25 to I29, all the values are same, which is all zeros. Similarly, I31 is also all zeros. So that is why we do not need to compare them. These are just redundant values. It does not make any difference. What makes a difference is this I30th bit and I12 to I14 func3 fields. Only these 4 bits help us decide what operation to need to be performed. Okay? So that is why we have in the ALU control, we have bit number instruction bit number 12 to 14, 12, 13, 14, and 30. In the hardware, we are just putting these 4 wires in the ALU control, not all the 32 bits. Okay? Any question? So you need to remember why we are having 12 to 14 and 30th bit. So I have already explained why the other bits in the func3 and func7 fields are, they are insignificant, and we do not need to have them for comparison to decide what operation to perform in ALU. Understand? Any question? Okay, so in your lab, in your simulation, you can just simply write this behavior, the control unit behavior with this is kind of if-else structure. You can just simply write ALU op equal 0. So what operation ALU should be performing? So based on these 2-bit input, you can generate the 4-bit output. That would be a control signal for the ALU. Okay. So we have talked about generating ALU op signal. Let's talk about generating the remaining signals, which are pretty straightforward. These are all 1-bit signals. Okay. So when reg write, so reg write is this. When it is deasserted, so as its name suggests, reg write means register write. Okay. When it is deasserted, deasserted means when it is 0. It means there is no effect on this register file. But when it is asserted, when it is 1, it means that we are writing data into the register file. So whatever the data at this port, it could be a garbage data, it could be a meaningful data, whatever it is here, it will be written into the register specified by this register number. Okay? Whatever the value RD we specify here, it will be, this data will be written at that address. Okay? You seems confused.
Yeah, you say about read write.
Yeah, so when reg write is 0, it doesn't make any difference. It will not be writing any data. Okay? When reg write signal is 1, it means that whatever data, 32-bit data present at this port will be written to the register. Which register? This register. Whatever the address we specify here. This is RD. Okay? So whatever data is available at this port, it will be written to this register. It could be like S5, S4, whatever. Okay? This is a 5-bit field coming from the instruction which specify the RD, destination register. Okay? Similarly, ALU source. So where is ALU source here? It is when it is deasserted or 0. Where do you think the second input of ALU will be coming from? From the register file. Okay? When this, what is this ALU source? This is a select signal for the mux. Okay? When this signal is 0, it means that it is forcing this input to appear at this output. Okay? So which means that the second input of ALU will be coming from register. When ALU source signal is 1, then it will be coming from the 12-bit offset field. I mean the 32-bit extended data. Okay? Understand? If you understand this concept, then do not get confused with these zeros and 1. I can swap this out, okay? In exam, you might see 1 here or 0 here, or 2 or 4. Whatever value is assigned against this port, it means that the select signal value should be that value in order to get this instruction, this data to connect to this input of ALU. Any question? Yep.
Just double check one more time. It is 0, it coming from registers, and then it is 1.
Correctly, yes. If it is 0, then it will come from the register file. But if I swap these values, maybe I can put 1 here and 0 here, then the behavior will be exactly swapped, okay? Which means that in that case, ALU source 1 means the data will be coming from the register file. Okay? And same thing is for all kind of multiplexers, okay? So you can just swap the values. I can swap the values, and you should concentrate on which value is written against which signal. Similarly, PC source and mem read. So PC source, what is the source of the next PC, next program counter? Okay? If it is the next instruction, which is coming from which is in the sequence, or the instruction which is the branch instruction. Okay? So the branch instruction, the decision will be made somewhere in between here, and this PC source signal will actually help us decide whether to execute the next instruction in sequence or the instruction given by the branch instruction. Mem read, when it is 0, it will have no effect on memory, but when it is 1, it means that we are reading the memory and the contents will be placed up here. What contents is specified by this address. Okay? Mem write, when it is deasserted, it will not do anything. When it is 1, then which means that we will be writing the data. The data at this port will be written, specified by this address. Okay? Mem to reg. So here again, we have just discussed. Mem to reg will decide whether data will be written to register coming from memory or from the ALU directly. Okay? Here you can see the values are 0 and 1, 0 and 1, but here it is 1 and 0. It does not matter. It could be in any order. Any question? Yep.
Sorry, but can you say that one more time about mem read?
Mem read here. Yeah, so mem read, as its name suggests, we are reading the memory. Mem read means if it is 0, then it means that it will not read the data from memory. Even if you provide the address, the value appear here is meaningless. It doesn't matter. When it is when it is 1, it means that we will be reading the data from the memory. Okay? So whatever address we specify here, the corresponding data will appear at this port, the valid data. Okay? Any other question? Yep.
What's the difference between PC source and just PC?
So PC source is a signal, is a select signal for the multiplexer, which selects which input to route at the output of this mux. Okay, so PC source will decide what is the source of the program counter, whether it's the next instruction in line, which is coming from here. If the PC source value is 0, it means that it will be executing the next instruction calculated by the current PC plus 4. Okay, if it is 1, PC source is 1, it means that the branch instruction has to be executed, and the branch address is calculated at this point. Okay, the current PC address and the offset value, okay, in the branch instruction. These are added together and the new PC is updated here. Okay, so PC source will decide whether to execute the next instruction in sequence or the branch instruction. Any other question?